Okay, good morning, good afternoon, or good evening to everyone. And today I'm going to do my final presentation for Illumination Optics subject. My name is Aditya Tandra, or in my Chinese name is Chen Yu Ming. And this is my outline for my presentation today. And my presentation for today is about an alternative approach for high uniformity distribution of indoor lighting LED. This project is, I believe it is from Vietnam Academy of Science and Technology in Hanoi. Okay, so now I'm going to introduce about the LED itself. And we all know that LED has been widely used in most lighting systems today because they have environmental benefits, such as it has low energy consumption, it has a compact volume, and it has a long lifespan compared to the previous light sources that we usually use, like incandescent or fluorescent light bulbs. So because LED is compact and easy to manipulate, it is suitable for smart indoor and outdoor lighting systems. And if we talk about indoor lighting systems, LED could influence humans' mood and cognitive performance by controlling the intensity and the color of the light. And as a result, we need high uniform luminances to do so. But it has one disadvantage. The radiation pattern of the LED itself is actually not uniform. If we look here at the graph in the right, the pattern of the illumination is actually circular. So it is high at the center, like when the beam angle is at 0 degrees, and at the edges, the illumination would be very, very low. Okay, so how do we fix this? So we believe that improvements in LED distribution patterns have been done by adding a secondary optical element in order to achieve the high uniformity. And we already know that original LEDs are considered Lambertian light sources. So there are 5 proposed mode methods that we already know by now so far, which is the first one, direct lit LED backlighting illumination using Lagrange interpolation. I don't know how to spell Lagrange. I'm sorry if I spell it wrong. And the second one would be freeform optical system. While this is usually applicable for roads such as freeway, etc. And the third one is by using uniform illumination system by service tailored lens and with the help of LED array configuration. So we need to find a correct configuration for LED array. So it is pretty time consuming, I guess. And the fourth one is the improvement of the second one, which is a 3-dimensional freeform lens. This is usually to obtain uniform rectangular illumination. And the fifth one, we use simple design lens for human-centric lighting using the LEDs. Okay, so what is the purpose of the research actually is to propose a method to accurately calculate illumination distribution based on superpositions of the 2 sidewall LED system. Well, the system here is I've put the picture at the right here. These are the 2 sidewalls, the left one and the right one. Okay, so how does it work? Firstly, we have highly non-uniform illumination distribution on the ceiling from the 2 LEDs. One on the left side, one on the right side, and then we want to know the dependence of uniformity ratio. This is L over H. What does L mean? L means the length of the ceiling, and the H means the location of the LED source from the ceiling. In short, it is like the distance between the ceiling and the LED. And then we rotate the LED at a small angle to overcome the low intensity near the wall. And therefore, low uniformity illumination distribution at the center will still exist. And from these findings, we need to propose an alternative model for several illumination configurations to obtain high illumination distributions. And therefore, we have to design a general guideline to design the LED indoor lighting system, which come up with 3 advantages, or maybe should I say 3 purposes. So that is for practical efficient lighting, and to assure that it is friendly to human eyes, and it would be very valuable enough for LED lighting manufacturing as well. Okay, and so we are now entering the next topic, which is the model and theoretical analysis. So we have this same image here from the previous slide, and we call this as our schematic of indirect lighting system. We have here the ceiling is made of material with diffuse reflection, so the ceiling is actually a Lambertian surface to induce the comfortable lighting. And the light source array here, for the longitudinal direction, they have to be arranged to obtain uniform distribution. But we don't need to consider anything here. We only need to consider transverse direction. Okay, so now we take the one from the left, and we have the schematic cross-section of left lighting system. Well, so as we can see from the graph here, the height of the LED from the ceiling is h, and then the ceiling has a total length of L. Okay, and it can be divided into n parts, and every part of the ceiling has a length of delta L right here. If we can see from the pattern of the light source for the perpendicular direction, it would be circular, but we don't need to consider it right now. So we just need to focus here in this direction. To get a uniform light distribution, as we can see, we need to get a large number of n, as large as possible, so that we can conclude that the delta Li here is proportional to the theta I, this large, the angle here. So we can obtain these 2 equations. The expression for alpha I, the angle from the wall to the delta Li, and the theta I. Okay, we have 3 assumptions to be made. The first one, the light source distribution would be spherical. And the second one, the flux density from source should be equal in all directions. And the third one is the light distribution on the ceiling for the I part of the intensity in the I part of the ceiling would be proportional to the delta Li. And we can get the following graph. This is for the 0.3 meters for the height, and then the 4 meter long for the ceiling. We can see from the left it has a very high luminance, and then it drops until the center, which is its illuminance is the lowest, and then it rises up again. And what can we get from here? Spherical pattern light source for uniform illumination is not efficient for indirect light systems, so we have to change this for sure. Okay, in actual system, we use the LED as a replacement for the spherical pattern light source. Since LED is Lambertian, we can get the following 2 expressions as shown here. And the graph of illumination distribution on the ceiling is now in a batwing shape like this. One note here is the half angle for LED is 120 degrees, and we can see on the very near on the regions very near to the wall, we call it as dark regions because it has on almost zero illuminance on these 2 sides. But if we shift 0.5 meters, the illuminance is at its peak. Okay, and we now tilt LED for 5 degrees, so that the LED line illuminates to the midpoint, and then we can see at dark regions they would have better intensity. Now the intensity is almost 0.4 at the so-called dark regions, and still at somewhere like 0.5 meters from the edge of the wall, the illuminance still reaches its peak. And then if we tilt LED at a larger angle, we can find out the dark regions near side walls might not have disappeared, but the uniformity ratio between the eye here center over IO, which is at the peak, its value would be reduced. We are now curious about how different height and length, ceiling length values would matter for this case. So we consider dependence of illumination distribution on these two variables. So we have 4 cases right here: case 1, case 2, case 3, and case 4. So for a constant H and then for larger L, we can see here that the illuminance at the center would be much lower, and then the bat wing shape would be much sharper, and the peak would be much sharper as well. And now if we keep the length of the ceiling to be constant, and then the height of the LED is changing, we can see that in the dark regions the illuminance will go up right here compared to this one, and then as well as the illuminance at the center. So what do we get from the picture, from the graphs? By modifying H and L values, we can see that for constant H and larger L, we can get a smaller theta I value and lower illumination, resulting in lower uniformity ratio. And for larger H and constant L, we can get a reduced theta I value between the center and the maximum, so we can get a higher uniformity ratio. How should we prove that the intensity is highly dependent on these two variables? We can see the graph here. Okay, so the first one, uniformity ratio. Here I send intensity at the center per maximum intensity is actually proportional to the length of the ceiling over the H. So of course we would consider a high ratio. But for indoor lighting system, the small number of H is preferred, so there is actually a trade-off. Okay, now we move on to the next topic. If we remember on the introduction, we have said that for smart and friendly human applications, we need uniform light distribution. What we can do now is to add a secondary lens after the LED, and then do the light intensity redistribution. And the redistribution should look like this. Here, illumination distribution is designed to achieve uniform overlapping illumination. Here, like in here at the center, it overlaps at the center. And we can get the equation for light distribution on the ceiling of LED system with secondary lens. And for the left side, it goes down. It has a negative slope right here, and for the right side, a positive slope. So from 0 it goes up. If we add the left and the right side, we always get the constant F0, a constant called F0, where F0 means the maximum illumination distribution or the maximum intensity of the LED source. We can see the total illuminance right here is always constant from the graph here. And the design of asymmetric lens, not symmetric, asymmetric lens along the side wall can be shown by the graph below. So it goes from here. It has, for small angles, it would have a large factor, and it will reduce as angle increases. So coming back here, at almost 90 degrees, so near the wall, we would need a very high redistributed factor, and we can introduce the redistributed factors, the capital L. For the left side, capital L is shown by the equation below, and for the right side, it has a similar equation. And this is the graph of redistributed factors of illumination through the lens. I'm sorry. Okay, so from here, what we can do now is we need to reduce light intensity at the peak, because unfortunately the peak is not at the center, but it is like somewhere almost approaching center, but not at the center, unfortunately. And then we have to enhance the intensity at the center of the ceiling to make it ideal for our case. Okay, so the light through the lens follows the following logistic function. This is the logistic function, with the L is the maximum value of the curve, and then K is the logistic growth rate. This is a constant, and then the X here is the position on the ceiling, any position, and then the X0 here is the midpoint position of on the ceiling. Okay, if we set, for example, K equals to 3, this is what we get. And from both LED lights, we can obtain a symmetric system. And because it is symmetric, the total uniform luminance overlap from both sides is achieved. And how about any other values of the K's? As we can see, this is the case for K equals to 1, and then this is for K equals to 2, K equals to 3, and 4, and 5. As K increases, the slope would also increase. But they overlap at the same point, always overlap at the same point, no matter how the K value is. So they always have uniform illumination on the ceiling, and it is at the center. And these two graphs represents the luminous intensity functions for various Ks. Okay, so now what we need is the second redistribution factor, this time for the secondary optical lens. And the redistribution factor is called RD. For the left side, the equation is as shown. And for the right side, it has pretty much similar equation. This is for the standard condition. H equals to 0.3 meters, and L, the length of ceiling, is 4 meters. If we narrow the L a bit, as the K value decreases, the peaks will shift to the right, and the sharpness of the curve, what I mean sharpness here is the sharpness shape, the shape of the curve looks sharp. It will be less sharp than the left one. And if we maintain the length of the ceiling, but we increase the H value, which is in which H means the distance of the ceiling and the LED light, we can get the fact that the redistributed factor values are lower compared to the left one. This is because we get higher uniform factors prior to the addition of lens, so it is more uniform even before we add the lens itself. Okay, so if we compare all 6 of these graphs together, we can get one conclusion. For constant H and larger L values, we will have the lower uniformity ratio. The lower uniformity ratio will result in larger RD factor, and not only larger, the value is also higher, the peak will also look sharper. But the curve shape for all these 6 cases are pretty similar. And then what is RD useful for? It is very useful in design construction of the lens. If the RD peak is too sharp, it is usually hard to design. So in various cases, there will be various optimum K value, and it depends on the real condition and what the LED application is used for. So we cannot generalize everything. And these are the conclusions. For the given wall washing lighting system, we use the addition of lens for LEDs to achieve high uniformity illumination, because as we all know, spherical pattern light sources will not work at all. And this is my personal point of view, because we know that the ceiling must be low enough to enable such a condition. We would prefer rooms with long ceilings. So the L should be large enough. And depending on the purpose, LED illumination is designed using the logistic function with growth rate coefficient K, and the various K values show various intensity illuminations, so the characteristics would be different as well. And even so, the total uniform illumination is still achieved on the ceiling, and particularly at the overlapping point, which is at the center of the ceiling. These are my references, mainly for pictures. And thank you for your attention. Have a good winter vacation, everyone.